Welcome all to lecture number 5 in Foundation of Astronomy course. Today we are going to discuss about stars and planets. First of all, we are going to discuss the formation of stars and planets. Stars and planets form as a part of the same process. The goal is to understand this process. We compare our solar system to others to test our model of star and planet formation. So first of all, let us discuss what is the composition of an atom. Atom consists of proton, neutron and electrons. Protons and neutrons are found in the nucleus, while the electrons surround the nucleus in a cloud. Electron can have only certain energies. Other energies are not allowed. You can find a book on one shelf or another, but not in between. You can look electron like that. The energy state of atoms are like shelves in the bookcase. We use energy levels to represent the allowed energy state of an atom. Each type of atom has a unique set of energies, typically illustrated with an energy level diagram. Now, the lowest energy state is called ground state. The energy level above the ground state are called excited state. The atom can go from one energy state to another, but never have an energy in between. Here you can see the figure, a visual analogy of what is happening. An atom with energy E2 decays to the lower energy state with energy E1. So what happens? It emits a photon, E photon equal to E2 minus E1. So the energy is coming out as a photon which carries an energy, that extra energy of E2 minus E1.
The electrons in an atom can only occupy certain states. So just like a person on the stairs who can only stand on particular steps. So I can stand down here on the ground level like the ground state of an electron, or I can stand up here on the first step. In the same way as an electron moves up and down through its energy levels, it has to gain energy. Electrons gain energy from the photons that fly by them. As an electron, I would stand here just surrounded by photons, all flying past me, all different colors, all different frequencies, all different wavelengths. I will completely ignore every single one of them until I get an electron of just the right energy to take me up one step. Now here I am up one step. If I want to come down again, I have to give up that exact same amount of energy in order to do that. I can't go up a half a step, and an electron can't go up half an energy step. I can't, once I'm up a step, go down a third of a step. Neither can an electron. There's nowhere to land. So you have to make full steps, whether you're a person on the stairs or an electron in an atom. Now I'm back in the ground state. It's possible for me as an electron to move 2 steps at once. But in order to do that, I need to collect a higher energy photon. I need a photon with more energy, a photon that's bluer. And then I can go up 2 steps all at once. From here I have a choice. I can either come down 2 steps, one at a time. If I was an electron, I would maybe emit a yellow photon and then emit a red one. Or, alternatively, I can get rid of that all at once and come down 2 steps. It's important to remember that the energy levels for an electron are not physically separated like stairs on a staircase. Instead, they're just different ways that the electron moves in the atom. So the ground state might be something like a slow dance, and the first excited state might be just something a little bit faster. And then it moves all the way up to its highest energy levels, and it has all kinds of crazy swing dancing going on up in its highest energy levels. To move down again, it gets rid of some of that energy, comes back down to the ground state where it's just sort of slowly dancing around the atom.
Now let us discuss what happens in emission spectra. An electron emits a photon and drops to lower energy state, losing energy. You can see a cloud containing many two-state atoms with energy E2 will emit photons with energy E2 minus E1 in all directions. When the light from the cloud is collected and passed through a slit and a prism, you can see the slit and the prism, the light shows up as a bright emission line at a wavelength corresponding to the photon energy E2 minus E1. The photon energy is equal to the energy difference between the two levels. Now, what is absorption spectra? An electron absorbs the energy of a photon to jump to a higher energy level. The photon's energy must be equal to the energy difference between the two levels for absorption to happen. A schematic is shown here. You can see a light source which emits white light. It contains all wavelengths. So if you see through a telescope, slit and a prism, you can see a continuous spectrum containing all the colors of the rainbow. Now, when this white light is passed through a cool gas containing some hypothetical two-state atoms with energy levels E1 and E2, the photon gets absorbed and the electron jumps from E1 to E2. So photon with energy E2 minus E1 is absorbed by the electron cloud, and what happens is that line will be missing in the continuous spectra of light. You can see it as a missing line. So this is called the absorption spectra. The wavelength at which atoms emit and absorb radiation form unique spectral lines, which is a fingerprint for each atom. You can see the visible emission spectrum for hydrogen, and when the same spectra is plotted with wavelength in x-axis and brightness in y-axis, you will get a figure like this. The emission spectra for helium, mercury, neon is also shown here, which is totally different from that of sodium. So we can say that each type of atom has a unique spectral fingerprint. Now continuing about absorption lines. For stars, astronomers look at the absorption lines in star spectra. These absorption lines help to determine a star's temperature, composition, density, pressure, and more. Now, a continuous blackbody spectrum which emerges from the hot interior of star, like what we saw, the white light from the bulb. As the radiation passes through star's atmosphere, the atoms absorbs photons of certain wavelength, causing absorption in the stellar spectrum. Atoms in the hotter outer atmosphere of the star may also emit photons, causing emission lines in the spectra of some stars. So we will have absorption spectra as well as emission spectra from the stars. Now this can give an idea about the temperature of the star. Temperature plays an important role in formation of stars and planets. There is a relationship between temperature and how much light an object emits at a specific wavelength called Wien's law. We have a video about Wien's law. Now a class question. Which color star would be the hottest? The answer is blue will be the hottest. Now let us continue on star formation. Now we are going to discuss about molecular clouds. Molecular clouds are large, dense clouds of gas, mostly hydrogen and dust. The molecular clouds experience self-gravity. The parcels of gas within a molecular cloud feel the gravitational attraction of all other parts of the molecular cloud, leading to a net gravitational force towards the cloud center. So that is called self-gravity. All parts of the clouds are gravitationally attracted to each other. The net gravity point towards the center of the cloud, which is a very important point. Now what happens eventually? Gravity wins over other factors such as pressure, magnetic fields, regions of molecular cloud collapse. And the collapse and fragmentation lead to dense star forming cores in molecular cloud, which is represented in this schematic diagram. Again, the molecular clouds continue to collapse under their own gravity, and the center shrinks faster and the outer layers later. This produces a dense protostar, which is shown in the figure. Now what happens? The protostar heats up due to the conversion of gravitational energy into thermal energy. And the collision between particles are such a way that they are pulled towards the center that raises the temperature of the core. You can see the figure. The cloud continues to rapidly collapse from inside out, with the falling material feeding a growing protostar at its center. Now the protostars are large and they are relatively cool. They will emit little visible light and mainly infrared light due to their cool temperatures. Infrared studies of molecular regions reveal protostars and their disk. Now there is a certain balance which is being created in this formation. At a given time, the protostar is in balance. The force from the heated gas that pushes outward and the force of gravity that pulls inward balance each other. And suggested we say assertion, gradual growth via gravity. So likewise, the gravitational force pulling the material, you can see, towards the center of a protostar is exactly balanced by the pressure. And likewise, as more materials falls into the protostar and as heat from its interior radiates away, the protostar becomes compact and the pressure in the protostar increases. The protostar continues to accelerate more material. The interior temperature and the pressure rises, and the energy is radiated away, keeping the balance between the pressure and the gravity. Now here we will talk about the core's temperature. The core's temperature and the density increases until nuclear fusion is possible. The thermal energy which escapes from the interior of a protostar is radiated into the space and the protostar contracts, and gravity becomes more stronger in the smaller protostar, increasing pressure and temperature. As the protostar gets smaller and smaller, its interior gets hotter and hotter. And in this way, protostar's gravitational energy is converted into thermal energy until the core gets so hot that hydrogen fuses into helium. The new star settles down, burning hydrogen in its core, and hydrogen begins to turn into helium and that's how a star is formed. Now, there is another classification called brown dwarf. If the critical temperature for the nuclear reaction that turns hydrogen into helium is 10 million Kelvin and the proton star is less than 0.08 mass of Sun, then there will be never a reaction, a nuclear fusion reaction going to happen. And such a situation we call it as brown dwarf. Now the young stars are surrounded by rotating disk of gas and dust. Why so? The rest of the solar system is actually formed from this rotating protoplanetary disk. So let us discuss about the disk. You can see the disk formation in this figure. So how this disk or the assertion disk is formed? It is actually due to the angular momentum of the system. We know the angular momentum of the system will be always conserved. And what is the result? A spinning sphere will become flattened rotating disk. The collapse is slowly perpendicular to the rotation axis but not parallel to it. So it is easier for the particles along the axis of rotation to fall to the center. So we can have a small video on the formation of assertion disk and protostar.
Angular momentum is a conserved quantity. That means that as long as no outside force is acting on a system, the angular momentum that it has will stay the same. The angular momentum depends on three things. It depends on the mass of the system, it depends on the rate of spin of the system, how fast it's going around, and it depends on how the mass is distributed within the system. So I'm going to demonstrate the way that the angular momentum depends on some of these quantities using this special low friction platform that we call the rotating platform of doom. Okay, so I gave myself just a little bit of a kick. I can feel myself spinning ever so slightly. So here I'm going around. I can push myself around against the friction, but I have to work really hard in order to get going against the friction that's in the platform, even though it's a low friction platform. So now I'm going to go ahead and I'm going to change some of those things that I was talking about. So I'm going to have Michelle go ahead and give me a little push to send me spinning a little faster. And now I have my mass distributed, so there's a lot of it toward the outside. My arms are out away from my body. What's going to happen if I change that distribution so that I bring my arms in toward my body? Well, you've seen ice skaters, so you should have an idea of what will happen. I should spin faster. So let me try it and see. Michelle, go ahead and give me another little push to get me going. And now I'll bring my arms in and I spin faster. And I push my arms out and I spin more slowly. And I bring them in and I spin faster and I push them out and I go more slowly. What I can do is I can go ahead and increase the amount of mass that's way out here at the outside. So now I have a lot more mass. So now I'm spinning even more slowly than I was before. And if I go ahead and ask Michelle to give me a little push, okay, I'm spinning again. Now we should see a bigger effect when I bring this mass in. And we do. I spin a lot faster than I did before. And now I put the mass back out again, and I spin even more slowly, and I bring them in, and I go fast. So the important thing to remember about angular momentum is that there are three things that matter. There's the mass, the rate at which the object spins, and how the mass is distributed. And if you change any one of those, one of the other two has to change as well in order that angular momentum is conserved.
So we have to remember that as gravity causes the collapse of a slowly rotating clump, it rotates faster The rotation slows the collapse perpendicular to but not parallel to the axis, so the clump flattens. Eventually, the clump collapses from inside out and an assertion disk and protostar is formed. Most of the gas lands on the assertion disk. The disk will have an overall rotation either clockwise or anti-clockwise due to conservation of angular momentum. So some of the material is ejected back into the space along the polar axis and they are called the bipolar jets. The material left behind in the disk forms the planets and other objects that make up the solar system. So you can see the schematic of these polar jets forming in the protostar. In this disk, the particles collide and stick. This leads to larger objects called planetsimals. Planetsimals continue to grow by collision and gravity, and these may form planets. So you can see the part of the protoplanetary disk closest to the protostar is hotter than the outer part. The inner disk has only material that do not melt at higher temperatures. So that is why we call it as refractory materials that doesn't melt at higher temperature. The outer disk has the refractory materials and volatile materials like ice. Volatile means that can melt and evaporate at moderate temperatures. So planet can actually gather gas from the disk. This makes the primary atmosphere, and low mass planet cannot hold on to their primary atmosphere due to their low gravity. Some low mass planets later emit gases from their interiors, producing a secondary atmosphere. There are four inner planets, that is Mercury, Venus, Earth and Mars, which are called rocky terrestrial planets. And there is four outer planets, they are Jupiter, Saturn, Uranus, Neptune. They are called gaseous Jovian planets. The asteroids, comets, dwarf planets are the leftovers of the planetesimal. Moons formed from the giant planet's assertion disk. The physical process, this physical process led to the solar system. That is what we model. And we see young stars with disk, extrasolar planets that are planets that orbit stars other than sun. Now we have to have a discussion about Doppler effect also. What is Doppler effect? The motion of a light source towards or away from us changes the wavelength of the wave reaching us, and that is called the red shift. It is called motion away, and blue shift, that is motion towards. So when the waves that reaches observer are spread out longer or redder wavelength in this side, and when the waves that reaches this observer, that is observer in the right side, are skews to the shorter bluer wavelength, that is higher frequency, and observer in the middle doesn't observe any Doppler shift, which I can demonstrate with a video.
We never travel fast enough to see the Doppler effect for light, but we often travel fast enough to hear it. And so I have brought with me the world's most annoying noise on a string, and I'm going to turn it on, and then I'm going to make it come toward you and make it go away from you. And I want you to pay particular attention to what happens as the noisemaker approaches and then as it goes away again. That's pretty annoying, right? So when it comes toward you, now, it sounds different than when it goes away from you, now. So what did you hear? As it approached you, you heard a higher pitch, and as it went away from you, you heard a lower pitch. Well, the same thing happens for light, that it gets shifted to a higher frequency when it comes towards you, that is, the light becomes bluer, and it gets shifted to a lower frequency as it goes away from you, that is, the light becomes redder. And so, what does this have to do with astronomy? Well, pretend that my right hand is a planet, and my left hand is a star. My head is the center of mass of these two objects. So the planet is out here and the star is right here, the center of mass, very close to the star. So now as these objects orbit, they're going to orbit the center of mass, each of them. So watch what happens as they move. So you can see that the planet and the star, here comes the star toward you and away from you, and toward you and away from you. If you were to watch the spectrum of that star, you would see the star get blue shifted as it comes towards you and red shifted as it moves away from you. The very first planets around other stars were discovered this way.
So you can see the video and understand the Doppler effects. Now, how these extrasolar planets are discovered? That is through the radial velocity method. That is the radial velocity method. Some stars have a periodic velocity change, and this velocity change can be detected by Doppler shift. You can see the stars, if it moves towards there is a blue shift, and if there is a star which is moving away from Earth, there is a red shift. So that is being schematically represented in these three figures. Now, another way of observing a planet is the transit method. That is, a planet passing in front of a star causes the total brightness of a star to decrease. The larger the decrease in brightness, the larger the planet. And another way is direct imaging. It is very difficult to see a fainter planet in a bright glow of its star. So it is very hard to find in a direct imaging technique. A few extrasolar planets have been discovered by this method. So likewise, many of solar system are not like ours. Many have hot Jupiter-sized planets close to the stars. Earth-sized planets have not been discovered have been now discovered by this Kepler spacecraft. So this is the discovery till November 2013. Now we will have a discussion about HR diagram or Hertzsprung-Russell diagram. It is a plot of luminosity versus temperature. It is the key to unraveling the stellar evolution and how stars change with time. So in the top we see the brightest, in the left we see the hottest. Some stars are cool but very luminous. Some stars are very hot with low luminosity. On the far left end of the main sequence are O stars, that is hotter, larger, more luminous than Sun. On far right end of the main sequence are the M star, which is cooler, smaller and fainter than Sun. The mass of a star determines its characteristic. So majority of the stars falls along the main sequence of the HR diagram. Most stars, including Sun, exist on the main sequence. Knowing where a star lies on the main sequence, you can determine its approximate luminosity, surface temperature, and size. So in this class, we have discussed about star and how the planets are formed, and they are formed of the same process. The gravity pulls most of the mass of the collapsing molecular clouds to the center and eventually forming a protostar and then star. The conservation of angular momentum flattens the rest of the material into a rotation disk, which is where the planets and other solar system objects form. And solar systems are now known to be common and show great diversity of planet types. So that is all for today's lecture. Thank you all for patiently listening. See you in the next class.